Let's welcome Joao Costa for the first research talk of this day. He's a PhD localized between Lisbon and Paris, under supervision of Pedro Ribeiro and Andrea De Luca. And today he's going to tell us about continuous measurement in diffusive classical systems. And Joao, the stage is yours.
Okay. First of all, thanks to the organizers for accepting me to give a talk here. So, as it was said, I'm going to talk about continuous measurements in diffusive classical systems. So, actually, the original motivation to look at these came from the quantum side, where measurements actually fundamentally affect dynamics of a quantum system in a completely different way than unitary evolution. And by now, it is well established that in many different quantum systems, such as random quantum circuits, if you increase the measurement rate past some critical value, you can get entanglement phase transitions, which means like below some threshold, your entanglement is very high, and above it, it's very low. And combining this transition, people have also studied learnability transitions, where below the threshold, the observer can barely get new information about the system, and above the threshold, they can. And so these learnability transitions, they can be, they only involve classical concepts, and so it would be tempting to look at classical systems to see if measurements on classical systems have these sort of learnability transitions. Of course, in classical systems, we wouldn't have one rule. It would be some conditional probability on the measurement outcome. Here in this talk, I won't follow exactly these paths, but rather I will see if measurements can affect some observer's description of transport properties of a classical system. And okay, what type of classical systems? So I will consider these lattice cases, which are essentially particles on a lattice that is described by configuration, where you have a bunch of sites that can be empty or occupied. And this configuration evolves stochastically in time according to some Markov process. I will always assume that my system is between two reservoirs that pump and remove particles at some specific rate to the system so that I can have a good definition of transport here. And okay, one example of such a system would be the simple symmetric exclusion process, where particles can hop to the left or to the right at the same rate, and they cannot, of course, occupy the same site. Two particles cannot occupy the same site. Or, for instance, the weakly asymmetric simple exclusion process, where on top of this SEP, I add some external field that puts this bias on the jumping rates. You can jump to the right, say, with a bit more probability than to the left. Here, L is the system size. Okay, so why looking at classical lattice models? First, because I mean there are a lot of quantum models, the open quantum models, that in the limit of strong interaction with an environment, they can be effectively described by these classic lattice models, and also because you can rigorously get rigorous results for these models. So, for instance, for diffusive models, such as the ones that I've just shown, if you rescale time and space appropriately in the diffusive scaling and you take the thermodynamic limit, you can effectively describe your system by some density and current field, which evolves deterministically in time according to your conservation of particles and this constitutive relation, which expresses the current as a function of the density. Now, of course, this is only true in the limit L to infinity explicitly. If you are at a very big L, but not L to infinity, you still have particle density and current fluctuations, which for these type of models can also, for some of these type of models can also be rigorously established, like this probability distribution. And in fact, you have this macroscopic fluctuation theory, where the probability of some path of some density and current profile is given by this path integral-like measure that is defined, of course, on the submanifold of particle conserving trajectories. So here, this U would be the action associated to this path integral. And okay, and the quick note. So because of the way the reservoirs act on the system, essentially the density at the left and at the right must coincide with the density at the system, and so this is another restriction on your path on your density and current profiles. Okay, so the plan of the talk is to first introduce the concept of continuous measurements and incorporate them in this MFT formalism, and after that, look at transport in these type of systems. So intuitively, when a measurement is performed, essentially you have some probe that becomes correlated with the observable you want to measure on the system, and then you look at the state of the probe. For simplicity, we let us assume that the probability of getting some state in the probe S is some Gaussian distribution centered around the true value of this observable on the system. Here, gamma quantifies the measurement strength. So if you take this to infinity, the state of the probe coincides exactly with the observable. And delta t is the time that you take to perform the measurement. In continuous measurements, you take this delta t to 0, but then you perform many measurements, and so you continuously extract information about the system. So what will we measure? So we could measure the local occupation on each site, but these wouldn't be consistent with this macroscopic fluctuation theory, but rather we will consider the coarse-grained occupation. So essentially, you have some length scale that is macroscopically small but microscopically big, and you measure the occupation on this length scale. Okay. So physically, you could understand this as if the probe doesn't have infinite resolution and it has some resolution scale. Okay, so let us now consider the setup a bit more concretely. So what is happening is that your system is described by some true configuration, C0, that evolves stochastically in time. And at the same time, Alice is performing these coarse-grained measurements of the occupation. And she gets the signal S. And the signal S, the probability distribution of the signal S is given by this formula here. But of course, Alice doesn't know the true configuration. So what Alice knows is the signal that she receives. So for Alice, she describes the system as the conditional probability of some configuration conditioned on the measurement outcomes that she got. And so if Alice knows Bayes' theorem, she can rewrite this conditional probability as simply the probability, or being proportional to the probability of some configuration trajectory, unbiased configuration trajectory, times some exponential factor that suppresses density profiles that don't match with the measurement signal that you got. So in the thermodynamic limit, you can rewrite this coarse-grained occupation simply as a density, of course, and you can write, and now you can write this conditional probability in an MFT-like formula where you have the MFT part to the action that comes from the unbiased probability plus some term that comes from the measurements. Now, the next step is a bit tricky. So essentially what we do here is we assume that the measurement signal that Alice saw is a typical one. So if you look at this formula here, essentially your measurement signal, I mean, there is a big L in front. So the measurement signal in the thermodynamic limit should be very close to the evolution of the density on your system. And this evolution of the density on your system is very close to the hydrodynamic equations by normal MFT. So in a typical realization of these, Alice will see some most probable measurement signal, and she will describe the system as such, where now rho asterisk is the solution to the hydrodynamic equations. So essentially, by what is happening here is that by measuring, by by getting this typical signal, Alice becomes more confident that the system evolved according to the hydrodynamic equations, or more close to that. And so this is essentially the action that we wanted to derive, and now we will compute everything that we can from it. And so, as promised, I'm going to look at statistics of the current. And so consider the following experiment. So we initialize the system at time t = 0 with 0 particles on the right reservoirs, and we let it evolve in time according to its dynamics, and Alice performing her measurements of the density on the system. So how confident is Alice that you have some, after time t, that you have some number of QR particles on the right reservoirs? This is the question. So we can restate this for the integrated current, which is simply this QR number of particles over time. And of course, we can write probability for this integrated current from this path integral measure that we derived, simply as such. Okay, where you have our action, the constraint on the particle number conservation, and having integrated current J. Okay, now you have this big parameter L in front, so you can do saddle point approximation. And essentially you get that the probability of some integrated current is given by e to the minus L. This is evaluated on the minimal saddle point profiles that satisfy the particle conservation law and this integrated current J. Okay, and since we want to remove any transient effects from these, we will consider also the limit of time going to infinity, and so you get an extra large parameter time, and you can write the probability of some value of the integrated current simply as this, where now all information is contained in this phi gamma of J function, which is called the current rate function. Now, since we did this, you can, in your action, you can actually replace the rho asterisk, which is the solution to the hydrodynamic equations, by the steady state of these, because now, I mean, this difference will become 0 when you put these inside this limit. And so this is important because now your action is time invariant. It has this time symmetry. And so, okay, and so another small note, sometimes we will be talking about this current Kuhlmann rating function, which is simply generally related to this current rate function by a Legendre transform, because from this function we can simply by taking derivatives compute Kuhlmanns of this integrated current probability distribution. Okay, so what interesting things can happen to these rate function or to these saddle point profiles? So, okay, for if your integrated current is close to the steady state average of your the current steady state average, then your saddle point profiles should be considerably close to your hydrodynamics steady state and inherit all symmetry from your action. However, if you have driving currents far enough from your steady state, something critical like spontaneous symmetry breaking can occur. Of particular relevance here is symmetry breaking of time invariance, where your saddle point profile is not time independent and it depends on time in some way, or if your system starts with some symmetries, say particle hole symmetry, for example, in SEP, switching empty sites for full sites, then you can possibly also have breaking of this type of symmetry. And symmetry breaking like these will eventually lead to dynamical phase transitions, which correspond to some non-analyticity in your current rate function or Kuhlmann rating function. Okay, so the additivity principle, which we will assume for what follows, essentially consists in assuming that no such spontaneous symmetry breaking in time of time invariance happens, and so your saddle point profile is time independent. And so this is very important because I mean, it brings a lot of simplifications. So now your density profile only depends on X, on space. By conservation of particles, your current only doesn't depend on time and on space, and so it becomes equal to the integrated current. And so you can simply rewrite your rate function as an action that now only has the space parameters lives in 1D and only has one field, the density, because now the current is just equal to the integrated current and doesn't depend on space and on time. Okay, so why should we do this? There are some sufficient conditions you can derive. For instance, if you show that your U gamma function is convex for some suitable choice of f, of some function, of some transformation f, then you show that there can be, the additivity principle is valid, and actually that there can't be dynamical phase transitions. And so this was done originally by Bertini, and they proved that for normal MFT, if this condition is satisfied, then you get additivity principle. We did the same process they did for our case with measurements, and you get this additional condition. And okay, I'll just say that both of them are valid for SEP without any external field. And okay, and so for now we will assume that all these convexity conditions are satisfied. We have this regular problem where the additivity principle holds, and you have a unique saddle point solution. And okay, we will further assume that your diffusion constant is 1, and you don't have an external field, so to avoid unnecessary complications. And from these you get this final action that you need to compute. If you want to do this numerically, the procedure would be to compute the saddle point that is consistent with these boundary conditions, plug it in the action, and repeat the procedure for different gamma and j's to compute this current rate function. We will do this for SEP. All our plots from now on, or most of them, are for SEP, because as we've seen, SEP satisfies these convexity conditions. Okay, so the first thing we can think of now that we have measurements is to see what happens if you take measurement strength to infinity. And so, of course, to minimize this, your saddle point density needs to approach the steady state value. And so from these, you see that your current rate function is just quadratic in your integrated current, which means that distribution is Gaussian. All higher cumulants vanish, and you just have first cumulant, the average, and the second cumulant variance that are non-zero. You may ask, so if you measure so strongly, how can't you know exactly everything about your system? Why do you still have some variance there? So an explanation for that would be that, okay, you know your density profile, so you know exactly, like if you split your interval in very small subintervals, you know exactly how many particles are inside this small subinterval, but you don't know exactly where they are and how many can escape the subinterval and how many entered. And if you think a bit, and you can see that if you keep the density constant and you take the limit t to infinity or t very large, your probability of the integrated current will simply be a Gaussian, centered around this average value and with variance given by the mobility. And now if you want to compute the full probability of some integrated current, you just need to multiply this on every subinterval, and you will recover the result we got from there. So note that if we had taken the measurement procedure where you measure every single site, you would know exactly everything that happened on the system, and you would know precisely the current, and you wouldn't have any fluctuation of the current in this limit. But this would be like a Maxwell-Demon situation where you would know everything microscopically, and so this wouldn't be consistent with this thermodynamic formalism. Okay, so here you see some plots for SEP converging to these quadratic functions. What happens if the mobility vanishes at the boundary? Then if the mobility vanishes at the boundary, then your current must be equal to gradient of the density at the boundary, but since your gradient of the density is fixed by your measurements, the current cannot fluctuate. And so what happens in this case is that also, besides all higher Qmans, your variance also goes to 0 in the limit gamma to infinity, and essentially, and only the average current is non-zero. Now, the obvious question to follow up on this is how do these Qmans approach 0 with gamma? So to do that, we must look at the saddle point profile, at the deviations of the saddle point profile to the infinite gamma saddle point. And we will do that first for the non-singular case. And okay, since I'm a bit low on time, I'm going to be a bit faster. And okay, just to get a picture of this. So essentially, if you consider rho hat as the solution that minimizes this function u gamma with unconstrained boundary conditions, when you take the limit gamma to infinity, this solution becomes much more favorable than the one that needs to satisfy the boundary conditions. And so what happens is that your actual saddle point profile, when you're taking this limit gamma to infinity, will approach this rho hat function in the bulk, but in the boundaries it will need to compensate and go to the correct boundary conditions. And so if you actually need to do this, if you actually want to perform this large gamma expansion, you need to consider the expansion on the bulk and on the boundary separately, and you need to rescale the boundary with square root of gamma. But then, you will conclude, if you do a bit more computations, that only at leading order for the Qmans, only the bulk expansion is relevant in this case. And essentially, from all the calculations, you can show that the Qmans rating function at leading order is of this form, and so that all Qmans decay to 0 as powers of 1 over gamma. So this was for the case where the mobility doesn't vanish anywhere. Now, what happens if the mobility vanishes at the boundary? Then you get a completely different thing. Okay, you still have these two expansions that you need to take care, but now at the boundary you need to rescale by a different power of gamma. And actually, now it's the boundary expansion that matters at leading order for your Qmans of the current. And from the boundary expansion, you can show that at leading order, your rate function is of this form, where okay, the quadratic form now has a log gamma in front, which gives the fact that your variance is going to 0 in the limit gamma to infinity. And if you compute the Qmans, now all Qmans decay to 0 as log gamma. So now in this singular case, instead of having, I mean, of course, all Qmans go to 0, but they go much slower than in the non-singular case. Okay, so just to conclude, before I conclude, I just want you to show now this. So what happens if the convexity conditions are not satisfied? Can measurements induce some sort of dynamical phase transition? And so a measurement-induced dynamical phase transition would look like at gamma equals 0, you don't have a dynamical phase transition. And if you increase gamma at some point, you will start having a dynamical phase transition. So we don't have any formal proof for this, but okay, if you look at your action, what the measurements are doing again is making the saddle point closer to the hydrodynamic equations, hydrodynamic solutions, which has all the symmetries of your action. And so you shouldn't be able to have a dynamical phase transition in this case. But can measurements change the order of the phase transition? And okay, and we will assume that we have the particle Hall symmetry that I talked about, but the additivity principle is still valid, so no spontaneous symmetry of time occurs, but symmetry breaking of time occurs. And so like this, the action is written of this form. And okay, one curious thing you can note is that this action is actually can be mapped to the action of a classical particle in 1D, where the density is essentially the position of the particle and the space is essentially the time. And this particle moves in such a potential, and essentially your problem is the particle starts at position n, and it does something, and it needs to end at time t equals 1 in the same position, and you want to compute the path that minimizes your action. And from these you can simplify your problem and show that actually you just need to minimize this function. Okay, that you need to minimize this function. And okay, if you do all these, you can see that for this model, the Katz-Lubavitch-Swan model, at some particular values of epsilon and delta, epsilon is essentially some attraction strength, you can have a change in the order of transition at gamma equals 0. Your transition is second order, so the first derivative is continuous. And if you increase gamma at some point, you get first order transition in your current rate function. Okay, and so with this, I'd like to conclude.
Thank you very much for this very interesting talk. I think that we are good with time, so are there any questions from the audience? Yeah.
So for the case of CEP, I didn't understand what was the difference with earlier results of current cumulant generating function.
Sorry, for the case of CEP?
For the case of finite CEP, I did not see what was the difference with the earlier results of the current cumulant generating function that was obtained through MF.
So you mean normal CEP without any external field when you put
the normal CEP,
yes,
and you just measure the current.
Yeah, okay, so
sites.
that we only studied the limit because that, as I said, you don't have any dynamical phase transition whatsoever. And we only studied the limit gamma to infinity. So we studied this in a very different scenario. And in this limit, we see, I mean, it depends on the boundaries that you put on your step. If you put 1 and 0, you have this mobility going to 0. And so you see this scaling for a very large gamma, this log gamma scaling. And if you don't have these singular boundary conditions, then your scaling is powers of 1 over gamma. But we didn't study these. I mean, okay, so we studied only in the limit gamma to infinity. CEP leaves at gamma equals 0. We didn't study the full curve going from one up to the other. But okay, it should be some continuous function mapping between one and the other.
Any other question from the audience? Well, maybe I take advantage of my privilege of being a chair, and actually I have a very simple question that is just a check. Are the particles hardcore, isn't it?
Yeah,
they cannot overlap.
Yes, they can't overlap.
Okay.
Yes.
And the second question is like you're using hydrodynamics also when you are measuring the state. Usually hydrodynamics requires some assumption and equilibration, while the measurements are trying to put you far from that equilibrium state. So
actually, the measurements are trying to
you're measuring the density. That's true.
Yes.
But immediately you're measuring the density not in a coarse-grained manner, but in a very localized manner. This will make some kind of noise that probably is not within equilibrium steady state. If you coarse-grain, of course, it's nice, but there will be some limitation of that.
Yes.
How can you be sure that you can apply dynamics here?
So if you just measure, you mean if you measure each site, for instance?
If I would measure on one site, I push the system out of standard equilibrium steady states. If I coarse-graining, I would be more gentle, but it would never be perfect. So how you can be sure that everything is consistent in assuming hydrodynamics while you're using the measurements?
So okay, so if you okay, of course, if you are in that limit where you just measure one single site or a couple of sites, then of course you're out of hydrodynamics, and every time you measure, I mean, you don't have an hydrodynamic description. But if you measure like in a course, I mean, what I expect is that as I increase the number of sites on which I measure, I approach slowly this regime where the hydrodynamic equations are still, the dynamic approach is still valid.
This I buy if you don't have the measurement. Measurement could affect this approximation. Like in other words, is the hydrodynamic approximation controlled? Is it checked numerically, or it is an assumption and you trust it?
Okay, essentially, yeah, we didn't check numerically that I mean, yes, that like SEP with, for instance, SEP measuring a bunch of sites and increasing the amount of sites I measure will go to this formalism that we're talking about. But okay, it comes from these things, from saying that in the limit, in these appropriate limits, these thing approaches the density.
And that I buy, definitely. I'm more worried about the diffusion equation, but we can chat later if you want. But it is very interesting. Thank you. Any other questions? No, well, let's thank the speaker again. Let's move to the next talk.